It's a pleasure to introduce Prof. Barenghi, who's going to talk about quantum vortex reconnections.
Thank you. So I'm going to tell you about reconnections in quantum fluids. This is work done by various people, students and visitors, in particular Simone Zucker from Verona. So my context is liquid helium and atomic Bose-Einstein condensates. These systems are quantum fluids. They are fluids which have no viscosity, so they are superfluids, and the vorticity is really equal to 0. It is confined to delta function singularities, space curves, so essentially filaments of no thickness. The vortex core is fixed, is essentially atomic, and the circulation around these filaments is fixed. So they're very, very simple systems. Vortices are only mini tornadoes like indicated, vortex lines. We have two models which we use to describe our superfluids. The first is the Gross-Pitesky nonlinear Schrödinger equation, which you see here. It is a quantitative model for atomic Bose-Einstein condensates, that is to say weakly interacting Bose gases, the famous partial differential equations, which we can turn into classical format. Essentially becomes almost the same as the Euler equation. The only difference is an extra term which we call the quantum stress, which is what essentially regularizes this equation with respect to the Euler equation. In particular, it performs the vortex reconnections, which I'm going to describe. The second model is the classical vortex filament model, nothing but the Biot-Savart law for a very thin filament, which you see written here. So I'm going to tell you about experiments and numerical calculations done using these two models. So the context is actually the study of the turbulence of a quantum fluid. In the last few years, we have learned very much about this, and I would like to show you what I mean by quantum turbulence by running this little animation. So let me explain what we see here. We have a periodic box. We have vortex rings which are injected into the system. We're actually mimicking experiments done in particular at Manchester. And these vortex lines, vortex ring, deform, interact, reconnect. And after a while, the injection of the vortex ring balances out the very small dissipation which we have in the system, and we create a statistical steady state. And we have learned, for example, that this kind of turbulence in some situations can reproduce some main features of ordinary turbulence, in particular the Kolmogorov spectrum, the statistics of the velocity, the existence of regions of high vorticity. So let me continue this just to give you a feeling for what is quantum turbulence. It's a can of worms, really. But I stress, remember that here we have no viscosity. The vortices are all the same circulation, the same core size. So it's a very simple system. We are looking at the skeleton of turbulence, perhaps. Right, I'll stop this.
And they reconnect.
And they reconnect.
Despite the viscosity.
That's right. So we'll go. So what I would like to do is to compare the reconnections in our quantum fluids with the reconnections in ordinary fluids. I've taken this picture from a recent paper in the physical fluids for two reasons. First of all, you can see here these solutions of the Navier-Stokes equation. You see two antiparallel vortices which undergo reconnection, and you notice that here the reconnection event is not complete. It's not clean in the same way as it is in a quantum fluid. And the reason is very simple. The vorticity is a continuous field. So there is a major reconnection, but there is also the formation of secondary bridges, so the process continues. In quantum fluids, vorticity is concentrated to discrete vortex lines, so we cannot have this in principle. The second feature which I would like to stress is that the typical distance between the vortices as they approach each other before the reconnection and then move away is different. The behavior before the reconnection is different from the behavior after. So what about the quantum reconnections? Well, I want to make to give you a brief history of this problem. The idea of reconnections was actually an idea of Richard Feynman in his seminal 1955 paper. That was before actually people knew about, for sure, about the existence of quantized vortices. Reconnections were proved, mathematically at least, by a paper by Koplik and Levin in 1993. They solved for the first time the Gross-Pitescu equation, and they showed that it contains reconnecting solutions. What you see in this picture is two vortices which are in 90 degrees from each other as initial condition, and you see how they interact, and eventually they reconnect. Well, more work was done later. There is only one article in which the problem was tackled analytically by Nazarenko and his student West, and he tried to get the shape of the reconnection. Unfortunately, actually, the radius of convergence of the expansion of the quantum mechanical wave function away from the reconnection point was rather small, so he did not really make much progress, but it is the only brave attempt to solve this problem analytically. Everything else was done numerically or experimentally. I would like to mention the work of Arts and De Vele in Eindhoven. At some point, they claimed that reconnections are universal. That is to say, during the reconnection, a cusp is formed, which is always the same, like indicated here. Essentially, the sum of all the angles is always the same. Well, a couple of years ago, we showed that this is not the case. We managed to reproduce exactly this universality, but it holds true only for the initial conditions, for the rather wide set of initial conditions which they used. It's not valid for other initial conditions, unfortunately, so the cusp is not universal. And there is another feature which I would like to illustrate, and it is the existence of the bridges, which I mentioned before. So what you're looking here is a numerical solution of the Gross-Pitescu nonlinear equation, and here we have two bundles of vortices. That is to say, two systems containing parallel vortices which are set at a given distance from each other, which are let to interact. So there is not just one vortex, there are many, so many quanta. And our surprise is that actually during this interaction of systems with many quanta, some features which are somehow results of classical physics appear. In particular, the formation of a bridge between the reconnecting vortices. So let me continue the animation. You see how the vortex filaments become very much twisted. There are Kelvin waves. There are many little vortex loops which are generated by the reconnections of individual vortices, and you will see like a bridge which is left and then snaps away, as you see now. So that is actually what we like to see in these systems, that when you have more than one quantum, you build up essentially classical behavior, essentially transition from quantum mechanics to classical physics. Now, more work was done recently, in particular by Bob Kerr, and he considered the reconnection of antiparallel vortices. So a problem which has been discussed recently is a vortex loop scenario. The idea that during the connections, a large quantity of tiny vortex loops are generated and fill the quantum turbulence. Another paper which is relevant was a paper by Konrad Bayer, who is here, and Thomas Lipniaki, who is here too, and their student Kursa. They studied the problem using various models, and they found that when the angle between the reconnecting vortices is tight enough, they get this cascade of loops scenario, as you see indicated here. Actually, all these results which you see depend on the initial condition which is given. We are not sure that they're all independent of the initial condition, so we decided to actually take a quantum turbulence system in a statistical steady state and measure these reconnecting angles, which is the typical way the vortices approach each other. Well, we had actually to discriminate two cases. I said that quantum turbulence seems to be similar in some situations to classical turbulence, and that is what in our quantum fluids literature is called Kolmogorov turbulence or semi-classical turbulence. But there is another regime which we can achieve, which is actually very different from classical behavior, which we refer to as Wiener turbulence. And you see here a PDF of the typical angles of reconnections. The red lines refer to the Wiener turbulence, so they tend to be rather anti-parallel, and the black lines refer to the semi-classical turbulence, so they are reconnections at small angles. The reason for this is that in the semi-classical turbulence, there are actually coherent bundles, coherent structures, vortices which are parallel to each other, and therefore tend to reconnect at small angles rather than pi, which is typical of anti-parallel reconnections. There is also an experiment. This is a fantastic experiment performed by Srinivasan and collaborators in Maryland. What they did was to use tiny tracers, essentially micron-sized tracers. It's actually solid hydrogen, tiny snowballs, which get trapped into the quantized vortices, and using lasers, they allow us to see the vortices. And they saw reconnections. You see some images taken with the laser. Essentially, what you see here is dots and how the dots move. And by joining the dots, like a game for children, we get actually information, for example, about the distance between vortices before and after the reconnection event. What they found is that the reconnection is time symmetric, and this is the scaling which was observed. We tried to reproduce these results using the two models, and I want to tell you what we got, because our expectation was essentially that we had a good way to test the two models, the Gross-Pitesky equation model and the vortex filament model, and we would have loved to see that the two models give the same answer. Unfortunately, they do not, and there is a reason for that, I think. So, a typical reconnection event is this. We have the usual anti-parallel vortex configuration, the solution of Gross-Pitesky, and you see the two vortices snapping together and moving away. But what is actually the distance between the vortices in this event? It's given here. You see that the distance versus time scales differently before and after. Actually, there is quite a difference. It's much larger than the statistical error which we have. And the surprise was that the Biot-Savart reconnections don't do that. The Biot-Savart reconnections, they have the scaling which was observed in the experiments. So that was the surprise, because we would have thought that actually the Gross-Pitesky model is a better model than Biot-Savart, but it isn't. So we are left with a puzzle. Why the difference between Gross-Pitesky and Biot-Savart reconnections, and also why the difference between the Gross-Pitesky model and the actual experiments? So it's a double problem. And let me now illustrate what is the possible cause for this difference. It really goes to the heart of the problem. So I want to show you this movie again. So you see the previous anti-parallel reconnection solution of the Gross-Pitesky equation, and here I've added a plane in the middle of the vortices where the values of the density are plotted. Remember that in this model, the vortex lines are hollow. The density is equal to 0, exactly equal to 0 on the axis. That is to say, the real part of the complex wave function and the imaginary part go to 0 together on the axis. And you see that at the reconnection event, a very strong rarefaction pulse, a sound wave, is ejected, not symmetric around the vortex reconnection point, but in a particular direction. Essentially, you see this burst of sound, which removes actually kinetic energy from the vortex configuration and sends it off to infinity. So we think that this is the crucial element which breaks the time symmetry between before and after in this problem. So I want to stress that we saw this effect actually years ago, but we did not appreciate it in this way. So, and I want to mention Mark Leadbeater, who was the postdoc who spotted it. He discovered this sound wave. It was difficult to find because it's not symmetric around the reconnection point. You have actually to look for it. So I'm coming to the conclusion. So the conclusion is the following. There are clearly some analogies between classical reconnections and reconnections of ordinary fluids, solutions of the Navier-Stokes equation, at least in the sense that there is a time asymmetry. In our case, it is caused by the acoustic emission. There is no viscosity in our problem. There is also the possibility of transforming kinetic energy into sound energy, which is what we see. Sound energy in these systems, where at very low temperatures means phonons, which means heat, after all. Like viscosity means heat. There is another analogy, which is when we have many quanta, sufficient number of quanta, the previous movie involved only 5, after all, not a big number, then some kind of qualitative behaviors which are classical appear. For example, the formation of the vortex bridge between reconnecting points. I would like to remember that reconnections of individual discrete vortex filaments have been observed. I think this is somewhat unique in fluid dynamics. There is the problem of the vortex loop scenario, which is very much open, and then we have this puzzle which I described, Gross-Pitaevsky, Biot-Savart, and experiments giving different answer. So why is that? Well, that is the tentative solution. Remember that the Gross-Pitaevsky model only describes things at very short scales, essentially the scales of the coherence, of the quantum mechanical coherence length. In liquid helium, it's about 1 angstrom. So when you saw the rarefaction pulse, the sound wave, the wavelength involved was perhaps 10 or 20 angstroms, no more. So it's very short. The typical distance between vortices in the experiments is of the order of 10 to minus 2, 10 to minus 3 centimeters. So it's really very much larger, about 100 times bigger. The typical size of the tracer particles, these hydrogen snowballs used in Maryland, is about 1 micron, 10 to minus 4 centimeters. On the scale of the micron, on the scale of the separation between vortices, the rarefaction pulse, the sound wave, is irrelevant. The density wave expands out essentially and fills the system, it disappears and vanishes on such a large length scale. So it's actually, we should not expect to see that it determines the motion on the scale of the micron. So really, this inconsistency between the experiment and the two models is exactly what we should expect. And at this point, I think I'll stop. Thank you.
Are there questions or comments? Yes, please.
So, do you think that, or if you were able to simulate with Gross-Pitaevsky larger separation scales, you would go to t to a half?
Yes. Unfortunately, it's easy to say yes, but Gross-Pitaevsky is a partial differential equation. So the biggest calculation of Gross-Pitaevsky was done in Japan. I think it was 4,000 cube. And we have actually to put discretization points to resolve the vortex score. At least, I would say, 10 points within a vortex score. So we are never going to see scales which are 100,000 times the size of the vortex score. But so it's out of reach. And we cannot come close from the other end, because the Biot-Savart law, which we're using, assumes by construction, by definition, that any length scale of the flow is much larger than the core thickness. So we cannot take Biot-Savart down to Gross-Pitaevsky, and for practical reasons, unless we discover a practical way to do parallel computing, quantum computing, we cannot take Gross-Pitaevsky to the limit of Biot-Savart.
Does this, the wave, the density wave, does it keep, is it generated as they move apart from the folding hairpin, or is it just the moment of reconnection?
It's the moment of reconnection, that's the problem. So it's very intense at the reconnection point, because at the reconnection point, psi, the complex wave function, is equal to 0. The axis of the vortex is psi equal to 0. So you see in this picture, there is actually the trace of the density, and it is plotted as a function of a coordinate which moves away from the connection point These traces are lifted on top of each other to give you an idea. So essentially, this is the density before the reconnection. This sharp, intense rarefaction wave is the reconnection moment, and then you see that the wave becomes less intense simply because it spreads, spherically symmetric as it moves out. And that is why I'm saying that it has no effect on things on the scale of a micron. It's simply, it's already invisible on a scale of, say, perhaps 50 angströms.
Well, I don't think that was Conrad's question, but he can correct me. I thought the question was, if you take something like two orthogonal quantum vortex tubes or lines in Gross-Pitievsky, and you run that calculation so that there are different separations, are you going to get this deviation from the 1/2 law, no matter what their separation? I think that's what your question was. Is that correct?
Well, we should let Conrad
I'm sure
decide.
it was, yeah.
Because if that's his question, then the answer is probably that this deviation from 1/2 is true, no matter what the separation is.
This would be very surprising, I think. Because okay, when
And
the
same.
separation is large, basically the sound emission stops. The sound emission is intense when you have a large curvature, which is infinite in the moment of reconnection, but after that, the curvature tends to zero and sound emission stops. So I see basically no reason why there should be deviation between Biot-Savart and Gross-Pitievsky at low curvature. Yeah, this term.
This term essentially becomes the ratio between this term, the quantum stress, and the ordinary pressure gradient vanishes for distances larger than the coherence length. So as you move away,
So it should converge to 1/2 law.
Other questions?
Maybe I have, I think it's just a proposal. It would be interesting from my point of view to compare and to say something about, say, twist. I know you said there is, in your case, you don't have internal twist, but you have torsion of the curve, and twist transfer under reconnection, I believe, will be a key ingredient in the transfer of energy.
yes.
And helicity, of course.
Yes, in fact, we did try. Now, the problem of the torsion is that it is a high derivative. In the case of the vortex filament model, it's already a high derivative, such a high derivative that it gives us actually some problems about being confident about the numbers which we're getting. In the case of the Gross-Pitievsky equation, it is harder. Because remember that we don't know what is the axis of the vortex. We have actually to interpolate the singularity in space, and the error is actually is significant. So until we develop a better vortex tracking algorithm, actually, we cannot do that. But this is what we hope to do.
I'm just wondering, so we know for helium, the GP model is not a very good model. And so I'm wondering if you're looking at the separation after the reconnection and the immediate stages after the reconnection, whether it would be worthwhile to look at a slightly modified GP equation with a different pressure density relation that's a bit more representative for helium, and what you would get in that case.
Yes, that is a very good idea. This equation, let me stress it, is a quantitative equation for atomic condensates. It produces the correct dispersion formula. For liquid helium, it doesn't, because it does not contain the rotor minimum. If we make this nonlinear cubic term an integral nonlinear term, we can actually match liquid helium's dispersion formula, so the model becomes more realistic. What you say is actually a good idea. It is actually a computational challenge, because we would have actually to integrate at each position of space and time that integral. In fact, it has been done in 2 dimensions, but not in 3. I think.
I'd like to ask you about the numerical teaching. For example, how you, so do you have any trouble to use, for example, Biot-Savart law? You regularize the interaction? How it's work?
Yes, the use of the Biot-Savart law in this context
Yeah.
actually started in the 80s. The person who really pushed that was called Klaus Schwartz, working at IBM, and various methods and techniques to do the tricky things, like the regularization of the Biot-Savart law, the reconnection algorithm, which is attached to the Biot-Savart law, were actually done and tested by various people. And we never actually come across a significant observable difference between various strategies. So perhaps we should simply say that we do not know enough to discriminate between the various models to do what you say, to be able to tell which is the best. They are all equivalent, it seems, from what we can tell and compare to experiments.
So, but you have a vortex line, yeah? So you must discretize this. So how you manage this? So you must keep the information about when you cut on the pieces of this. So
yes, to give you an idea, the discretization is variable in space and time. So we need more essentially the Lagrange discretization points. We need more points where there are regions of very
no problems.
Yeah. No problems. We can actually, the big improvement of the last couple of years is that we can actually compute this very fast. We use the same tree algorithm which is used for computation of essentially gravity, like colliding galaxies. So otherwise, this integral essentially scales like n squared, because to move one point you need to consider all the others. Classical probing of gravity. We run it n log n, essentially with tree algorithms.
I have a question myself, but we're almost by time. Have you tried to integrate whatever you got backwards? Because from this equation looks reversible in time. If you have a phenomena before and phenomena after that you cannot recover when you go backwards, therefore you lose some information, which is we know, as you said, in the acoustic waves, etc., etc. So if you take your scheme and you integrate backwards, what happens?
I don't know the answer. I expect that we are not going to get the same because we have vortices, so they will be chaotic, and we'll never be able to essentially go through the same numerical procedures exactly backwards. And in the case of the GP equation, this sound wave really scrambles things because it's a wave there.
It's there. Okay. Thank you very much.